Yeah, and feel free to post questions on Piazza over the next week or so, right? Finally, we have finite elements. So in finite elements, the basis, the basic thing is that we are solving a problem when the solution is a function, and to make that simpler, we want to restrict the solution into a subset of possible functions. I mean, that subset of possible functions is called a function space. And we have studied the function space that composes of piecewise linear and continuous functions, right? We split the space into finitely many elements, and we're studying all functions that are piecewise linear and continuous across the interface. That's the type of finite elements, the flavor we have studied in this class. So a basis is a set of functions within the class of functions when you can use them to perform linear combination to get any function you want within the space. And again, we have studied a particular basis that's we call the nodal basis. It's the set of functions that are equal to 1 at one particular grid point and equal to 0 at all other grid points. So this is the one element in the basis function, and the second element would be 0 here, but 1 here, and go back to 0. So this is the set of functions we use to perform linear combinations to get any function we want in that space. And so instead of solving for a function, we can then solve for the unknown coefficients multiplied on these basis functions, right? That converts a problem where the function is an unknown into a problem where a set of numbers are the unknown. So that's why the basis is useful. Now, how does finite element solve an energy minimization problem? So if I write an energy minimization problem and the unknown is a function, right? Finite element solve it by, first of all, restricting the possible functions into this class of functions, piecewise linear and continuous functions. And I'm going to turn that optimization problem from a optimization problem of functions to optimization function of the unknown coefficients multiplied on these basis functions, right? And then I can derive what the objective function is in terms of these unknown coefficients and solve this optimization problem by taking derivative with respect to the unknown coefficients. Okay, so a very similar procedure works on what's called the weak form of PDEs. And how to turn some simple PDEs into weak form, we have discussed this equation. To turn it into weak form, I multiply this equation with a test function v. So v is another function that lies in the same space as the space of u's, and integrate over the whole domain from 0 to 1, for example. And then I perform integration by parts. On this term. And the result is going to be, if I have 0 boundary conditions, the result is going to be minus of integral dv dx times du dx. Dx plus integration vf dx is equal to 0. It is called the weak form because it has a weaker requirement on the differentiability of u. So instead of having to be twice differentiable, the weak form only requires you to be once differentiable. That makes it possible to use this set of basis functions, this particular function space, right, to solve the problem. Because this function space is differentiable really only once. The second derivative would have a bunch of delta functions, which it's difficult to deal with. All right, so this is the weak form. And so how does finite element solve weak forms, right? So it's basically by plugging in these different different elements in the basis into the test function v to get a finite set of equations. And then we represent the u also as an unknown linear combination of the basis functions. And this finite set of equations is going to help us solve this finite set of unknowns. Finally, boundary conditions, right? So we studied the two types of boundary conditions. One type is a fixed value boundary condition. The fixed value boundary conditions really just to help fix the coefficient of the unknown solution v, right? So you basically get some coefficients that are removed from the unknowns. Well, the other type of boundary condition, is a derivative boundary condition. So the derivative boundary condition doesn't give us a reduction in the unknowns, but it is going to change the weak form because the integration by parts is going to give us some additional boundary terms. So the weak form has additional term that we have to take care of in the finite elements.